Great. All right. Thank you again for joining us. Today, I'm really glad to have our speaker, Dr. Nikki Nielsen, coming all the way from Australia at very early morning hours to talk to us about CGM research. So just really briefly to introduce Dr. Nielsen, she obtained her PhD in 2015 from New Mexico State University and moved all across the globe to Australia, and then also gradually switched from absorption line spectroscopy-based research of diffuse gas into now, as you will see, that her latest work on trying to dissect the complex gas kinematics using emission, 2D emission maps. So I very much look forward to your talk. So why don't you take over?
All right, yeah, thank you for the introduction. And I'm happy to see quite a few people online, including quite a few people at NMSU who I haven't seen in a while. So yeah, today I'm going to be talking about this galaxy that you see here in particular. So this is one of the galaxies as part of our DUVET survey, which I'll get into in a bit later. But we have mapped out some portion of the circumgalactic medium around this galaxy in emission. I know there's lots of CGM experts on the meeting, but I'll just go over some basic properties of the circumgalactic medium. So we know that the baryon cycle governs galaxy evolution. In order for galaxies to sustain their star formation, they must accrete metal-poor gas from the cosmic web. That often comes in along these thin filaments and adds angular momentum to the disks of galaxies. And then that star formation in the galaxy ejects metal-enriched gas along the minor axis, where that gas can then later fountain back onto the galaxy to form new stars and continuously build up the mass in galaxies. At some point, the galaxy will stop accreting all of that new material, and it will use up all of its star-forming reservoir and become quiescent. And so understanding how this baryon cycle works is really important for understanding how a galaxy goes from star forming to quiescent. And the circumgalactic medium, or the CGM, hosts and influences all of these gas flows that take place in the baryon cycle. So just to quickly define the CGM, it's the interface between the interstellar medium and intergalactic medium. The gas is bound to the galaxy and located out to about a virial radius from the galaxy. And it's diffuse and multi-phase, so we know it spans quite a wide range of densities and temperatures. And then the CGM also contains a large fraction of the baryons in galaxies. So at least 50% of the baryons are expected to be located within the CGM. And the CGM contains a gas mass that is actually greater than the gas mass in the ISM. Because the CGM is so diffuse and quite extended, we typically observe it using quasar absorption lines. So we've done this for several decades at this point. And that's where you have a bright background source, in this case a quasar, whose light passes through the CGM of a foreground galaxy. That gas then imprints absorption onto the spectrum, and we get all this great information such as kinematics, densities, metallicities, etc. And the great thing about quasar absorption lines is it's sensitive to low density gas. However, a big problem with quasar absorption lines is that we typically only get one single sight line per galaxy, and it only subtends a parsec-sized region around that galaxy, whereas the CGM has a much larger area around the galaxy. So we're kind of missing a lot of the gas. But regardless of this, we do know a lot about the low ionization CGM at low redshift with quasar absorption lines. And so I wanted to just highlight some things we know before getting into emission, because we can actually compare the new emission maps to what we know from absorption. So I'm going to just focus on the magnesium-2 absorption doublet, because that's what I have mostly focused on in my absorption research. So magnesium-2 is, it traces gas that is metal enriched and low ionization. So this is the cool CGM. It has a temperature of about 10 to the 4.5 Kelvin. It traces a wide range of H1 column densities. So quite a lot of different environments are traced by this absorption line. And it's very easily observed from the ground in optical wavelengths. So over redshift range of 0.1 all the way up to 2.6. And magnesium-2 is often attributed to all of the different baryon cycle gas flows that I mentioned on an earlier slide. So the cool CGM, we know that it has high covering fractions. So we typically see about 80% of sightlines within 50 kiloparsecs have detected magnesium-2 absorption. So there's gas everywhere. When we look at the absorption strength of magnesium-2 as a function of distance from the galaxy, we see that it decreases as you move outwards, but also that most of the gas is found within about 60 kiloparsecs of the galaxy, or about a third of the virial radius. Now, I mentioned that there's only a single quasar sightline per galaxy in most cases. So each one of these points is a separate galaxy quasar pair. And so that is actually causing quite a bit of scatter in this relation. And so we know that different galaxy properties actually cause this scatter. So the biggest one is actually mass of the galaxies. So when I color the points by their halo mass, we can see that the points separate out by mass. So the lower mass galaxies tend to hold their CGM closer to them, whereas the higher mass galaxies can have a larger CGM because their gravitational well is bigger. And so when we normalize out this mass by dividing this impact parameter by the virial radius, so taking into account that mass, we see that scatter collapse and the mass variation goes away. So another thing that can cause scatter in our quasar absorption line statistics is where that gas is being probed around the galaxies. So we can measure the azimuthal angle, which is the angle between the galaxy's projected major axis on the sky and the quasar sightline. And so when we look at a plot like this, so this is the number of galaxies as a function of that azimuthal angle, we typically find that magnesium-2, so this black curve, magnesium-2 tends to be located within about 20 degrees of the major axis and about 50 degrees of the minor axis. So if we go back to this very simple illustration of the CGM I had at the beginning, we tend to associate this major axis gas with accretion and that minor axis gas with outflows. We can also go back to that absorption strength versus impact parameter plot and separate out the major and minor axis gas. And what we find is that for a given impact parameter, the minor axis gas has stronger absorption strengths as well. And so this could just be due to if this gas is outflows, then maybe the gas has larger kinematics, the gas is more metal rich, there's just simply more gas along those sightlines. So taking into account the location around the galaxy can also reduce that scatter that we have. And we do think, based on the kinematics, that we are probing these different baryon cycle processes. So this is work done by Stephanie Ho, and I know she gave a talk in this series earlier last year. So if we focus on the major axis sightlines, we compare the velocities of the magnesium-2 absorption to the galaxy rotation curves, we tend to find that the low ionization CGM is consistent with either an extended rotating disk or these filaments that are coming in and adding angular momentum to the disk. And I also want to highlight work by a student working with myself and Glenn Kapsak here at Swinburne, Hasti Nategi. She has looked at this for H1 as well as a full range of other ions. And she's finding high co-rotation fractions there as well, but that the co-rotation fraction decreases as you move up in ionization. So have a look at her papers if you're interested in that. If we instead look at minor axis gas, we can compare, this is work by Schroeder et al., we can compare the absorption profiles that are observed to what are simulated if we assume that the gas is being ejected as a bicanonical outflow along the minor axis. And it seems to be well modeled by these outflowing bubbles. So the kinematics seem to suggest this accretion and outflow difference along the major and minor axes. Another thing that could be useful for distinguishing the different baryon cycle processes is metallicity. And so work by Wada and Leonard et al. Have looked at the metallicity distribution of typical CGM absorbers and they found a metal poor branch and a metal rich branch. So the metallicity distribution is bimodal, and we typically associate these with, again, accretion that's metal poor and outflows that are metal rich. And this is seen in simulations. So this is a lustrous TNG, where the map shows you the gas metallicity, and this is an edge-on galaxy. And so the highest metallicity gas is actually in these outflows along the minor axis, whereas this lowest metallicity gas is coming in along the major axis. So we're seeing it in the simulations, but the problem here is that we're not yet confirming this observationally. So this is work done by Stephanie Poynton, who was a student here at Swinburne a couple years ago, working with myself and Glenn. And she has this plot of metallicity as a function of that azimuthal angle. And what we would expect if we were to see this simulated galaxy map, we would expect to find a clumping of points down here that's metal poor along the major axis. That would be the accretion. And then we would expect another clumping up here that's metal rich along the minor axis that's outflowing. But her points are all quite scattery. And we think this is actually due to just the quasar absorption line method and how we've measured the metallicity here. Because simulations are showing that along that quasar line of sight, there's a lot of different structures. And so we've taken a total metallicity here. And so we're actually averaging across all those structures. And so we're kind of biased towards any metal-rich gas that is located along that line of sight, and we're kind of missing out on the more metal poor stuff. So there is some work where people are starting to break up the absorption along the line of sight and look for all of those structures. This is work that I'm thinking of Samir in particular, who's been doing this. So that's a promising avenue to investigate this further. But I mean, while we know a lot about the CGM from quasar absorption lines, we still have the difficulty that we still only have one sight line per galaxy, and we're getting large scatter in CGM properties, galaxy to galaxy, because we have a range of galaxy properties in our samples, and we also have a range of structures along that sight line. So how do we improve our observations and move the field forward? So there's a couple different ways. So we can get more sight lines around galaxies, but we also want maps of individual galaxies where we can fully control for the mass, the star formation rate, and the location around the galaxy. So one way to do this is to use background lensed objects. So you can use quasars where you have multiple quasars behind a single galaxy, or you can use background lensed galaxy arcs to spatially map the CGM along that arc. So in this illustration here, you could get absorption all the way around this ring here. This work has been done by Mortensen as well as Lopez and Tejos a little bit. So this Mortensen paper have a couple hundred absorption sightlines through this foreground star-forming galaxy. And there seems to be some interesting outflow structure here. But there's also work by a postdoc here at Swinburne, Tanya Baroni. She's using the Astro 3D Galaxy Evolution with Lenses survey, where they identified background lenses that are background objects that are being lensed by foreground quiescent galaxies, and using machine learning. And so she's looking at a couple different systems here at the moment. So hopefully her work starts coming out very soon. We do have a paper undergoing review at the moment. Another improvement is to use background galaxies rather than quasars to get more sightlines around a given galaxy. Galaxies are obviously less rare than quasars, but they are quite a bit fainter. And so to do this, we actually need bigger telescopes. So the 30-meter class telescopes will be very useful for this sort of work. But you could also stack the galaxies and lose a little bit of information there, but that's still a very powerful method for probing the CGM. And so this work here is by Zhang et al., where they stacked SDSS galaxies, and they looked for H-alpha flux in emission around the foreground galaxies. And what they found is emission going all the way out to about a megaparsec from these SDSS galaxies. And it has this interesting power law slope of r to the -2, which will be interesting a bit later when I show some emission results. And then another improvement that we could use is to actually stack the galaxies themselves and look for emission that way, because emission in the CGM is going to be extremely faint. As you can see here, we're getting fluxes that are going down to 10 to the -19, all the way even within a couple tens of kiloparsecs. So stacking the galaxies gives us a sense of what the emission looks like around more local galaxies. Although this method, you do have to be very careful about orienting the major axis of these galaxies in order to get a sense of the distribution of the gas relative, so the major and minor axis orientations. But this was really exciting work when I saw it last year. However, we actually don't need to stack galaxies to observe the CGM and emission. We actually can use instruments that are already on telescopes. So we have MUSE on the VLT, and then we also have the Keck Cosmic Web Imager on Keck. And so this is quite exciting. We know that the CGM is observable in emission because these two instruments are, in my opinion, currently revolutionizing CGM science. So we know at the highest redshifts, these are observations with MUSE up here and KCWI down here. So these are redshifts greater than 2, where you can pick up Lyman alpha emission around these galaxies. And they tend to find emission going out to at least 15 kiloparsecs from the galaxies in this work. And then this paper attempted to find an azimuthal variation in the Lyman alpha emission. And they did find one there as well. But the problem with Lyman alpha is it's a resonant emission line, and so interpreting the structures we see with this is a little bit tricky. At lower redshifts, so redshifts greater than 0.4, we are starting to see these large scale outflowing structures. So you can do this with magnesium-2, which also is a resonant line and suffers the same problems as Lyman alpha, but there are some really interesting structures here. So Zabel et al. Found these bipolar outflows around what's a fairly typical star-forming galaxy. And then Burchett et al. Found isotropic outflows around what seems to be maybe a post-major merger. And then at slightly lower redshift, work by Rupke et al. Actually used the O2 emission line, which traces a similar temperature gas as magnesium-2. So this is still the low ionization cool CGM. But they found these really beautiful hourglass outflows around this major merging system, going out to about 40 or 50 kiloparsecs away from the galaxy. So all of these maps are beautiful and they're great, but the thing that's still kind of missing from these maps is resolving the galaxy properties in order to connect the outflowing launch sites to the outflows themselves. And it's also difficult to get any small scale structure in the CGM and try and understand the cloud sizes in the CGM. So this is where our survey DUVET comes in. So DUVET is a blanket you put on your bed, and we're basically measuring the covering fraction of outflows in the disks of galaxies. So we have these fun logos that are a bed with a DUVET cover on them. So the idea is we're getting spatially resolved maps of outflows in local galaxy disks. So DUVET stands for Deep Near UV Observations of Entrained Gas in Turbulent Galaxies. This acronym is contrived. We came up with DUVET before we came up with the words that make up the letters. But the idea here is that we have a sample of about 30 galaxies that are local analogs of redshift 2 star-forming galaxies. So these should have an active baryon cycle where they're actively forming stars and accreting material. So this is our sample. We can see that on a plot of star formation rate versus stellar mass, we have galaxies that are starbursting. So their star formation rates are 5 to 15 times the main sequence value represented by the SDSS galaxies here. We have a range of stellar masses from 10 to the 9 to 10 to the 11. And these galaxies are quite compact. So they have half-light radii of about 1 to 3 kiloparsecs. And that's simply to be able to fit them onto the Keck Cosmic Web Imager's field of view. And these galaxies are nearby. So they have redshifts ranging from 0.015 up to about 0.03. So we're able to get spatially resolved maps of the gas in the disk. So the idea is that we will connect the local star formation rates in the disk of the galaxies, as well as other properties like star formation efficiencies, gas mass surface densities, pressures, etc., to the larger scale outflows that we see off of the disk of the galaxies. So we'll test star formation theories, map those outflows, and trace the transfer of gas between the ISM and the CGM. So I'm going to focus briefly on 3 galaxies in this talk today, where RS-08 is the primary one where we have CGM observations. But we do have work, we have a couple papers that are in work in progress looking at the rest of the galaxies as well. So these are 3 of the galaxies in our sample. So we have a set of galaxies that are more face-on. So this is RS-08. I forget the name of this galaxy, but it's quite beautiful. We have 2 papers on RS-08 so far, and then we also have a subset of galaxies that are more edge-on. So one is Markarian 1486, and we also have 2 papers there. So just to run through a couple interesting results from the DUVET survey. Here is work done by Alex Cameron, who's a postdoc at Oxford. And what he did is he measured the O3 4363 faint auroral emission line and used that to get metallicities of the gas within the disk of Markarian 1486, which is this beautiful edge-on galaxy, and about a kiloparsec or so above and below the disk. So over here is that metallicity map. And what we see is that along the major axis, we find the lowest metallicity gas, whereas the highest metallicity gas is located along the minor axis on both sides. So we have this picture here where we've traced the full baryon cycle in this galaxy, at least very close to the galaxy, where the low metallicity gases are these very metal poor inflows. And then we have the minor axis metal enriched outflows. So that was quite exciting to see. And it's important because this 4363 line gives you the electron temperature, so you can go directly from the observations to metallicity, whereas some of the other observations require some photoionization modeling. All right. Moving off of the disk of Markarian 1486, this is work done by a PhD student here at Swinburne, Daniel McPherson. He'll be submitting his thesis within about a month or so. But what he has done is he's taken the full KCWI field of view. And this is a map of the velocity dispersion measured with the O3 emission line. So this is still the cool CGM around this galaxy. You can see the disk of the galaxy. It has a low velocity dispersion within this box here. But then along the minor axis, we see these higher velocity dispersion kind of bubbles above and below the disk. And so Daniel identified the boundaries of these outflowing bubbles. He actually did it with just the surface brightness maps of O3, but you can also see it in the velocity dispersion where the emission lines are actually quite complicated. He can fit several Gaussian profiles to that absorption, where he seems to be seeing these the edges of an outflowing bubble. But he measures an outflowing opening angle of about 20 degrees, which is pretty typical for starbursting galaxies in the local universe. They tend to have opening angles of about 30 degrees. Quite interestingly, when he looked at the disk of the galaxy, he actually found quite a bit of blue shifted emission off of the disk of the galaxy. And so this is actually disk edge outflows. So this is gas that is coming off of the edge of the disk and towards the observer. And they have outflow velocities on the order of a couple hundred kilometers per second. And so it's important to account for this disk edge outflow because when you measure the mass outflow rates, so how much mass is being ejected by this star formation, while the typical outflowing bubbles above and below the disk make up most of the outflowing mass, the disk edge outflow consists of about 25% of the total mass outflow rate. And so if you're only considering the gas that's going above and below the disk, you're still missing a considerable amount of material that's coming off of the galaxy. So that was a really interesting result that we did not expect with this survey. All right, moving on to our face-on sample. So this is RSO8. This is work done by Braun-Reichert-Schuh, who was a PhD student here at Swinburne, but she recently moved on to Durham as a postdoc. And so this galaxy was actually the first galaxy we observed for DUVET. And when we observed, when we looked at the gas in the disk, we found these very asymmetric emission lines where Braun was able to fit this narrow ISM component, but then we found these very broad, very blue shifted Gaussian components in the emission. So this is just the 035,007 line again. And by fitting these lines, she was able to measure outflow velocities and mass outflow rates across the entire disk of RSO8. So she found outflow velocities on the order of a couple hundred kilometers per second, which is pretty typical for outflows in the local universe, and then pretty significant mass outflow rates. But more importantly, she found outflows across, I think it was about 90% of the disk of this galaxy. So rather than that canonical picture we have of M82, the most famous local starbursting galaxy, where you have these biconical outflows where the outflow is launched only from the center of the galaxy, IRSO8 is actually launching outflows across the entire disk. And so that is quite exciting. But we can actually go beyond DUVET. So while we have all these really interesting results, they're very close to the galaxy. So at most about like 6 kiloparsecs away from the galaxy, which is very near. But we know from quasar absorption lines that outflows can be found out to several tens of kiloparsecs away from galaxies. And so we were motivated to go beyond our DUVET survey and directly image the CGM around some of these galaxies. So this work is in collaboration with these people here. These are a subset of the wider DUVET team. So the DUVET PI is Deanne Fisher here at Swinburne. We also have Glenn Kapczak here at Swinburne, and then John Chisholm at UT Austin, Chris Martin at Caltech, and then I've already mentioned Braun, and then we also have Karen Sandstrom and Ryan Rickards-Vaught at UC San Diego. So these people were specifically involved in observing the CGM and emission around our pilot galaxy. So we focused on RSO8, so the galaxy that Braun was studying, because it was the first galaxy we observed for DUVET. But also we know, or we suspect that it should have an active baryon cycle. It should have a healthy CGM, and we should see lots of gas around this galaxy. And we know this because RSO8 is starbursting, as I showed from Braun's work already. And we know that it has a metallicity that is 3 times lower than is typical of its mass. So this galaxy has recently acquired a significant amount of metal poor gas to dilute its ISM metallicity. And so that gas would have then fueled the current starburst that we see. RSO8 is also interesting because we know from VLA H121 centimeter data that not only, so RSO8 is in this bottom corner here, not only does it have a nearby companion, which actually doesn't seem to be influencing the kinematics of the disk of IRS-08 at the moment because it's quite a bit smaller. But we know that there's a considerable amount of gas in the CGM around this galaxy. So this here is a plume of H1 going between IRS-08 and its companion, and it has quite a large column density. So if you were to put a quasar sightline through this plume, it would be considered a damped Lyman alpha absorber. So one of the strongest types of absorbers we know of. And so we wanted to look at the ionized gas around this galaxy to see if it is consistent with maybe gas that's accreting onto IRS-08 and associated with that neutral hydrogen that we see in the BLA data. So here is IRS-08. This is just an HST image that we obtained for this program. And this is, again, the H1 BLA data, the contours here. So just to make sure everyone's on the same page, IRS-08 is a nearby starbursting galaxy. So it has a redshift of 0.02 and a stellar mass of 10 to the 10 solar masses. So it's roughly an L-star galaxy. It is mostly face-on, so it has an inclination of about 15 degrees, and it's quite compact. So 90% of its optical light is actually located within about a radius of 2.4 kiloparsecs. And then I forgot to mention, but the H1 plume actually contains most of the neutral gas in this system, of 70%. So that this plume actually contains more gas than the H1 within the galaxy itself. So we did 5 different pointings with KCWI. So this is the integral field spectrograph on Keck. That at the time we did the observations was only blue wavelengths from 3500 to 5500 angstroms, but it now has the red side as well. But with these observations, we did our inner DUVET pointing. So that's this one right here, where we only spent 20 minutes on the galaxy. And then we did 3 pointings on this H1 plume that were 2-hour exposures each. And then we have a 4th or a 5th pointing that is off of that H1 plume to be used as more of a control field to see if there's any azimuthal variation around this galaxy. All right, so this right here is a surface brightness map of the 035007 line. So again, this is the cool low ionization CGM, traces gas that's about 10 to the 4 Kelvin. So it's quite similar to the magnesium-2 absorption we saw at the beginning of the talk. And then each of the bins you see in these maps has a signal to noise ratio of at least 7 on this emission line. I will note, I don't plot the inner DUVET pointing, but that's just because it would be a solid yellow, and I think it's more important to see the galaxy itself. But regardless, we found CGM emission everywhere we looked, and it goes all the way out to 30 kiloparsecs from the galaxy. And we were actually quite surprised by this. When we were planning the observations, we were saying, oh, we'll just have to bin the data. We might have to do 2 bins per pointing and just look for emission. But clearly, we did not have to do that. We actually have quite a lot of signal, and we actually have a little bit of small scale structure in the data as well, which we haven't yet had a chance to investigate. But that's coming soon. So when we talk about the CGM, we typically talk about how the absorption strength changes with distance from the galaxy. We, of course, see that plot every time we're at a CGM conference. So we can do something similar with the surface brightness with 035007. So here is surface brightness as a function of distance from the galaxy. The points are colored by where the gas is located on the galaxy. So here the blue points are basically within the disk of IRS-08. The purple points are the ones that are on this H1 plume, and then the cyan points are off the H1 plume. And so what we find is that the surface brightness decreases with distance, as we expect. We see emission all the way out to 30 kiloparsecs, which is about 1/3 of the virial radius, which is really the inner CGM, where we have found most of the magnesium-2 absorption in previous work. But more interestingly, we don't see a variation in azimuthal angle. So the cyan points actually overlap with the purple points. So the ionized gas we're probing here is doing something differently than the neutral gas in this system. Another interesting thing to note is the shape of this profile. So we went in and we fitted two different curves to the data. So within the disk of the galaxy, we fitted an exponential to the ISM, and then the CGM was more well modeled by a power law with a slope of r to the minus 2. And so what we think we're seeing here is actually a transition between the ISM and the CGM at about 4 kiloparsecs, or roughly twice the 90% radius of optical light around this galaxy. So as you move outwards from the galaxy, the gas changes properties between the ISM and the CGM. And I don't think anyone's really seen that before. So this was quite exciting. We see it in O3 because we have an IFU, we have multiple lines. So we also see it in the O2 doublet. The slope of the CGM is a little bit more steep. And we also see it in H beta, where the slope is a little bit more shallow. But this slope is comparable to the H alpha emission SDSS stacks I showed at the beginning of the talk. But again, the ionized gas is behaving differently than the neutral hydrogen in this system. So the H1 remains elevated out to large distance, whereas the ionized gas is decreasing. And so we think what's happening here is the ionized, so the H beta and the H1 are tracing different structures in the CGM. Not quite sure exactly why yet. Because we have multiple lines, we can start to look at line ratios. So here is the ionization from the O3 to O2 ratio as a function of distance from the galaxy. And we find that the ionization decreases in the ISM with radius because you're moving away from the H2 regions that are photoionizing the gas. And then it levels off. And then once you get into the CGM, we find increasing ionization with radius. And this increasing ionization is similar to what is found in absorption. All right, so what exactly is happening here? Why is the ionization mechanism changing in the CGM? So we can look at line diagnostic ratio plots because O32 in particular depends both on the ionization and the metallicity. So here we're looking at O32, so the ionization is a function of metallicity. And what we find is that the RS08 disk, so the ISM, is consistent with typical SDSS galaxies, but then the CGM points come off of that relation and start to behave differently than the ISM. And when you compare the CGM points to photoionization tracks where the gas is being photoionized from H2 regions, the CGM emission is not behaving like we expect from those models. So the CGM is not being photoionized by H2 regions, which isn't a big surprise because we don't expect a lot of star formation in the CGM. But what about shocks? So we can look at a better, like a shock diagnostic plot. So this is O3 to H beta as a function of O2 to O3. Again, the RS08 disk is consistent with SDSS galaxies, but then the points in the CGM all come off of that relation. So it's, again, behaving differently. And when we compare those points, especially with the inner points, so within about 10 kiloparsecs of the galaxy, we find that the CGM seems to be consistent with low velocity shocks, where this is probably just the interactions between the CGM and the outflows that are coming out of the disk of the galaxy. But then as you move further and further away from the galaxy, the points come off of the shock models. And what we think is happening there is that the extragalactic UV background starts to take over. And that's not unsurprising because we typically assume that the CGM is ionized by the extragalactic UV background in absorption. All right, so given that we've seen all of this gas, can we make an estimate for the mass of this cool CGM from these observations? So this is just a reminder of the baryon budget of galaxies inferred from quasar absorption lines, where we expect to find the cool CGM making up about 35% of the baryons. So we can make some assumptions. There's these assumptions all have problems, but we make them. So we assume the gas is cool, 10 to the 4 Kelvin. We assume a smooth gas distribution, that the gas is not clumpy. We assume that power law slope that we found in the surface brightness profile holds all the way out to the virial radius. We assume there's no azimuthal symmetry, or there's no azimuthal variation around this galaxy, which is probably okay because the galaxy is face-on. We're not picking up outflows and accretion like we would in an edge-on galaxy. And then we assume a constant density, electron density of 1 in this case. So given all these assumptions, we measure a total CGM mass of 10 to the 10.5 solar masses, which is actually comparable to what is estimated from absorption lines and L-star galaxies. So how does this compare to the other components of RSO-8? So we know that it has a stellar mass of 10 to the 10 solar masses, and its H1 mass is 10 to the 9 solar masses. So it seems that the cool CGM in this galaxy has a mass that's comparable to the stars in the ISM, which kind of works out with the baryon budget there. But there's a considerable amount of uncertainty in the density. In particular, absorption tends to find electron densities of about 10 to the minus 3. But emission does trace more dense gas than absorption. And so we can what we actually do in a revised version of our paper is we take the mass estimates from the absorption lines and back out constraints on our electron density for emission. So stay tuned for that. But there's other uncertainty in all of the assumptions that we've made here, like azimuthal variation and that the gas is quite clumpy as well. All right, so just to finish up, IRSO-8 is only one galaxy. So I just wanted to highlight some very preliminary results looking at a second galaxy that we have in our Beyond DUVET survey. So this is Kisser 1578. It's actually this object right here. So this is a more edge-on galaxy. It might actually be a little bit irregular, but it has a similar redshift. It's a slightly lower mass than IRSO-8. It has a star formation rate of 3.7 solar masses per year, so it's quite a bit lower than IRSO-8, but it's also a lower mass galaxy. And then we do have ALMA data for this object, but we have not analyzed it, so I don't have those maps for you yet. But here are the KCWI pointings we used around this galaxy. So this inner pointing is our DUVET edge-on pointing, where we only spent about 20 minutes on that galaxy, but then we spent 1 to 2 hours with KCWI focused primarily along the minor axis and the major axis of this galaxy to try and look for signatures of those outflows and accretion along these axes. So here is a very preliminary surface brightness map of the O3 line. Again, the signal to noise ratio is greater than 7 in every bin you see here. And I will note that these two outer pointings, the normalization is a little bit off because the sky subtraction needs work. But we do see emission everywhere we observed, out to about 40 kiloparsecs. And there seems to be some interesting structure very near to the galaxy as well. So what does the surface brightness profile look like here? This is it. So the blue points are on the galaxy, the purple points are along this major axis, and the orange points are along the minor axis. So we do seem to see a little bit of azimuthal variation where some of the major axis points have elevated surface brightness compared to both the minor axis and the other side of the major axis. So there seems to be a little bit of something there. But also, we still kind of see that exponential profile within the disk of the galaxy, and then that power law going out further. So it's possible that we still see a transition between the ISM and the CGM here. I just haven't done the fitting yet to get where that is occurring and compare that to IRSO-8. All right, so what's next? So ideally, we do this for more galaxies. We do have 2 more galaxies with observations like this that I have not yet reduced and looked at, but preliminary looks do find emission basically everywhere we observed again. It would be nice to get galaxies with a range of star formation rates with these emission maps, because we've been focused on the starbursting galaxies, which might have a special CGM that's where there's more gas and it might have different properties than more typical star-forming galaxies. It would be nice to get more spatial coverage around these galaxies because, as you saw, we don't fully cover the CGM around these galaxies. We are strategically picking our locations to best probe the gas flows we expect to find. And then also, it would be really nice to start doing this for UV emission lines to be able to compare more closely to the absorption we see. And I know Aspera, led by Carlos Vargas, will be looking at this with 06, but it would be nice to get a wider range of lines as well, and on bigger telescopes with wide IFU instruments to be able to do this quite efficiently. All right, just to summarize, CGM emission maps are here now, and they're quite exciting in my opinion. So I know the decadal survey really focused on getting these sorts of maps, but we're doing it now, and hopefully they become better in the future. So I showed that we found a clear boundary between the ISM and CGM in IRS-08 and potentially in a second galaxy as well. And that the CGM gas seems to be ionized by shock heating or the extragalactic UV background. We need some more lines to be able to explore this a little bit further. And then we estimated a very uncertain gas mass, but we really need to constrain the electron density of the gas around these galaxies to be able to get a more accurate mass, or maybe a more realistic mass as well. So thanks for your attention, and I hope you're excited about all this work. Thanks.
Thank you.
Thank you so much for a wonderful talk. I'm going to take over the Q&A for this session, and I see that there's already a hand up, but please, if you have a question for Nikki, do raise your hand using the reactions button, and I'll try to call on people in the order that they have asked questions. All right, and so with no further ado, Young, go ahead.
Yes. Beautiful talk. I'm really enjoying this. So, what's the spectral resolution of KCWI? And you haven't talked about the kinematic informations in those, especially. I'm really interested in the H1 plumes that you discussed. That you see that the H beta on the ionized gas and the H1 plume are kind of different from each other. So I was wondering if you have looked into the kinematics and if they're different in that way as well.
Yeah, so the spectral resolution of KCWI depends on your settings. So for the inner CGM, for the inner DUVET pointing on the disk of the galaxy, I think we had a resolution of 1800. So it's quite low, but then in the CGM, it's much lower. So we actually can't, for example, resolve the O2 doublet in the CGM that has an R of 900. So we can't really measure like a velocity dispersion in the CGM with these observations, but we can measure a velocity. And I do have velocity maps. I just don't tend to show them because I still haven't quite interpreted the data, because this is a quite quite face-on galaxy, and so it's a little bit confusing. But so this is the velocity map with O3. So you can see the galaxy is rotating. There's a little bit of interesting structure here, which I think is just a very like a satellite galaxy merging into the galaxy. But we do see this trend of like blue shifted gas close to the galaxy, and then it kind of goes red shifted a little bit. Don't know why. I did compare these kinematics, which the H beta is very similar to the H1 kinematics, because the Cannon et al. Paper that made the observations, they do have kinematics there. And I recall that they are quite a bit different, but I don't remember what order of magnitude they're different by. So it is different in the kinematics as well.
Yeah, so a quick follow-up. So when you said they are different, my first thought is maybe in the ionized gas you're probing and the H1, they are not co-spatial, because perhaps you're probing the ionized gas during the whole CGM, and the H1 is maybe like a sheet of filaments.
Yeah.
near the center. So that's kind of the picture I have in mind. That's why I asked about the kinematics, but thank you. Yeah.
Yeah, I think I agree with you there. I just don't know like how deep the H1 data go. And again, we also don't know how much of the gas emission that we're probing, where exactly that is along our line of sight.
Yep. Thank you.
Oh, sorry. Next up is Todd.
Yeah, this was quite interesting. I basically really had the same comment, which it seems to me that the most natural explanation of your H1 and ionized gas discrepancy is that it's projection. If you have an outflow with a large opening angle, and this one has kind of a disk-wide outflow, is that right? Anyway,
Yep, it does.
You could cover the whole thing with ionized gas that's basically up above where the H1, I mean, that's consistent with the rest of the story where the cool gas is coming in along the major axis and the ionized gas is coming out on the minor axis. That would seem to explain what you're seeing here. So I was just basically wondering if what your thoughts are about that interpretation.
Yeah, so we argue a little bit in the paper that it doesn't seem, we don't think outflows are dominating the CGM emission. And that's because the opening angle of starbursting galaxy outflows in the local universe tends to be quite small. So it's like 20 to 30 degrees. It should still be quite confined around the galaxy. But again, we don't know how far these outflows are going. Also, where we're able to measure an electron density, we find quite low electron densities, whereas outflows tend to have electron densities on the order of a couple hundred per cubic centimeter. So that kind of points against it as well. But I mean, looking at these kinematics, you could argue that this blue shifted material is that outflow, and then this higher or larger radius red shifted material is maybe that outflow kind of fountaining back down. I don't know for sure. It's a possibility.
Okay,
I hope that answers your question.
Sanj.
Hi, Nikki. Really very exciting results. Thank you for sharing it. I have a very similar question, but more broader in the sense that I wanted to see how you reconcile what we know from quasar absorption studies of magnesium-2 that you showed earlier, the idea of extended disk-like accretion flows and then the outflows from what you see in emission, and if you see the CGM ISM boundary, and if where do you see the two kinds of observation tracing in the big picture of the phases?
Yeah, so I think with the emission observations we have so far, we haven't yet found well, we've clearly found outflowing signatures in like the kinematics and other properties, but we haven't found accretion yet. And I'll highlight this kinematic map of our Edge-on galaxy, which is very preliminary work as well. So based on the work by Stephanie Ho, you would expect to find that the major axis gas would be co-rotating out to large distance with the galaxy. But this system is quite messy. There's, for some reason, this very blue shifted bunch of gas here. So I'm not quite sure what's happening here, but it probably just needs a little bit more work. But I think a clear signature of accretion in this case would be that red shifted, blue shifted, and in the same direction as the galaxy there. Now, the transition between the ISM and the CGM. So we do have a paper, Glenn Kapsak wrote it in, I think, 2013, where we have data going down to, I think, just a couple kiloparsecs. And in that case, the profile just kind of levels off, and you find kind of a constant absorption strength going into the disk of the galaxy, which seems counter to what we're finding here. But I think the difference is that emission and absorption are tracing different parts of the CGM. So absorption is focused on the very low density gas, or it's sensitive to very low density gas, whereas the emission is only sensitive to the highest density gas. And so there's probably something there with like how the gas is clumping and what exactly we're picking up with the two methods. So there's still a little bit of well, of course, there's a little bit of discrepancy there, and I'm not entirely sure how to resolve it just yet. But I think the answer lies in the fact that we're tracing different gas densities with the two methods.
Thank you.
Okay, Nick.
Very interesting talk. I wanted to ask, what is the extent, I don't know if you showed on the last galaxy that you're looking at, what was the extent of the auroral oxygen-3 emission? Do you have measurements of that?
On the last galaxy I showed, so
Yeah, I know
this
it's
one.
preliminary. Yeah, I was wondering if you were able to get that.
So we haven't looked at it for this galaxy just yet.
Because it raises
Definitely
the
something.
follow-up. Yeah, it raises the
Yeah.
follow-up if you want to go with a small slicer and get some high resolution measurements, especially in the inner regions.
Yeah, this one in particular, I think would be really interesting. So we can look at it for all of the DUVET galaxies because we do cover the line, but we've only really looked at it so far in the one galaxy. We're kind of low on people power at the moment.
Fair enough. Yeah, because I suppose that would answer the questions about density and temperature.
Yeah,
Thanks.
at least very near to the galaxy. Yep.
Yeah.
Okay, and the last question, you go.
Thanks. This is a very interesting talk. Can I just a quick technical question in the slide when you compare H1 and the is the H1 coming from H beta or actually from 21 centimeter?
The H1 is coming from 21 centimeters. So the orange points I show here are actually the column densities that I've just scaled down to roughly match the
Got it. Is there
points.
anything that you can push to a smaller radii?
Say that again, sorry?
Are you able to go into, what's the thing that stops you from going to a smaller radii?
Here, I think just the contours that are available.
Okay.
Because I don't have the H1 21 centimeter data. I've actually done the silly thing of just mapping out the points using an online thing because we asked John Cannon for the data, but he couldn't find it. So unfortunately, I can't explore it a little bit further.
Got it. Thanks.
Okay, and with that, we have reached our hour. So I would like to thank Nikki again for this incredible presentation. These data are super exciting. I love to see CGM and emission. So yeah, see everybody in another month or so for Jitie.